So now we're going to be talking about Chapter 4. And in this chapter we deal with some tools that are commonly used in theoretical chemistry. Perturbation theory, the variational method, and point group symmetry operations. In the perturbation theory section of this chapter, I go through the derivation of the common Rayleigh-Schrödinger perturbation theory. And then we treat some examples of applying this theory to, first of all, some simple problem where you can do all the integrals and necessary evaluations analytically. Basically an electric field applied to a linear polyene, a particle in a box model problem. This is to calculate the induced dipole moment and the polarizability of the polyene. And then we treat a Stark effect electric field applied to electrons in an atom and show how this can lead to ionization of the atom. And this is an important tool these days in methods, in experimental methods such as ZK, zero kinetic energy electron spectroscopy. And then we move on to talk about another application of perturbation theory, and this is the electron-electron interactions in atoms. Then when we move on to talk about the variational method, again I go through a derivation of the most commonly used linear variational method that gives rise to matrix eigenvalue problems. And then we treat some simple example problems that you can solve by hand. Then there's quite a bit of time spent on point group symmetry, and I choose to use the C through V point group of ammonia as an example because this is a point group that has some degenerate representations, and it's important to learn how to deal with these kinds of cases. In this chapter we deal a lot with treating vibrations of molecules as well as linearly combining atomic orbitals to form symmetry adapted orbitals. We introduce what are called projection operators, which are devices that allow you to form the correct symmetry adapted combinations of either atomic orbitals on atoms or molecular atomic displacements on the individual atomic centers that give rise to different symmetry adapted vibrational motions. We also deal with the concept of direct product representations. That is, when you have, for example, a product of two orbitals, each of which has its own characteristic symmetry, then the symmetry of that product of orbitals has something to do with the product of the symmetry of the two individual orbitals, and this is called direct product representation theory. Then there's quite a bit of time that I spent on time-dependent perturbation theory. The most commonly used application of this, of course, is in spectroscopy, and I do go through that. That is the treatment of an external electromagnetic oscillating field interacting with an atom or molecule, inducing electronic transitions in that atom or molecule. But I also treat in this in this particular section, the time-dependent perturbation that's due to the collision of, for example, an ion with a molecule. So here it's not an oscillating electromagnetic field, but instead it's the time-evolving potential that the ion exerts on the molecule as the ion approaches the molecule from a distance, comes closer, and then eventually recedes into the distance again. And then, of course, there's a summary to the chapter at the end.